name is Min-Kyu Paek from Clausthal. I'm a professor in Institute of Metallurgy now. This is my second the presentation in GTT users meeting. Actually, right after the appointment last year, I had a presentation about how we developed the steel database in FactSage. But today I'm going to discuss about the new suggestion using the modified Quasichemical model, which only we can use in the FactSage society. That model can be used for the molar volume prediction for the liquid alloys. So we select one of the ternary system, titanium, vanadium, aluminum alloy system, because it's very high strength and lightweight and corrosion resistance. So it can be used for the aerospace applications. But as you can see, this figure is not easy to make this kind of the shape by cutting or machining. So the additive manufacturing, 3D printing of the alloy is one of the promising technology. But we have to understand what is the kind of the agitation during the laser exposure. We should understand the kind of the circulation of the liquid alloys. So that can be governed by the Mellangoni effect, by the concentration change. And also concentration will change the volume or density, so we should have buoyancy, and then some Lorentz force, we also consider that. So we focus on the surface tension and volume at the beginning. So as you can see, we should understand what is the surface tension. So all the surface tension can be explained by the kind of the bonding between atoms. So we should have the free, the surface bonding, and then it will be contribute to make a shape to minimize the Gibbs energy. And also some contribution underneath of the bulk side. We also need to consider the interaction. So in our case, using modified Quasichemical model, we can explain that using the thermodynamic the parameters like enthalpy or entropy data to calculate the surface tension. But we also need the volumetric change depending on the composition when we have binary or multi-component system. And also alloy design people, they don't consider the soluble oxygen. So they consider that we have really clean alloys without any contamination, but it's impossible to completely remove the oxygen dissolved into the liquid aluminum or titanium. For example, if you have very, very small single ppm or 10 ppm of oxygen, you can form some kind of the oxide phases. So yeah, that should be also considered. Very, very strong affinity with oxygen, with the transition metals or aluminum. We have to consider that. Because of very, very strong affinity, it's not easy to reduce the titanium oxide or alumina or the vanadium oxide by hydrogen. So we have to increase very, very high temperature to reduce that. But at the same time, the oxygen dissolution will be occur every time. So using modified Quasichemical model, we can solve this problem. We can easily describe that phenomena. So compared to this ideal mixing entropy, we added this correction term. So if you have very, very strong affinity, for example, oxygen, we should have this kind of the short-range ordering. And then this short-range ordering effect can be considered by this equation. So that should be the non-configuration or entropic effect. But we have to multiply the temperature term here. It means if you apply this one, if you have more short-range ordering A, B pair more, your probability of the selection of A and B will be changed. So modified Quasichemical model consider this short-range ordering effect and then multiply temperature. It means you can decrease the temperature dependent term of your excess Gibbs energy. So it can be dramatically decrease the additional binary ternary parameters and with temperature dependence. That's why you can use FactSage database using modified Quasichemical model for the 10th order system or 20th order system without any additional multi-component model parameters. So we can secure the reproducibility and accuracy together. And also we try to apply this interpolation method to calculate the Gibbs energy in the ternary system. Depending on the intrinsic property of the binary system, if you have some very strong affinity with other element, we can also consider the system as a symmetric. So, but without considering this one, sometimes you can have mathematical failure. You can read the Arthur Pelton, one of the FactSage developers' paper about this geometry of the ternary calculation of the Gibbs energy. So from 2014 or before that, we tried to apply this modified quasichemical model for the liquid alloy system. So for example, oxygen with adding aluminum, we have to explain the oxygen content change of the liquid alloys in equilibrium at alumina phase. So from Fe to aluminum over the entire composition range is possible to explain the oxygen behavior. Carbon should be similar from iron to nickel rich side. All this pair distribution can be, the sum of this pair distribution should be calculated by the carbon concentration and oxygen concentration over the entire composition. And then in the binary system, one special equation in the fact stage, you can change the coordination number in the liquid binary system depending on the composition of the liquid alloys. So all the other thermodynamic tools, they always fix the coordination number. So they have to add, to have the asymmetric property, they have to add first order, third order parameters. But in our case, intrinsically, we can consider this one and then decrease all the parameters. So this is one of the example. The Bragg-Williams random mixing model with the symmetric system, they added a very, very big 50 kilojoule for the enthalpy data and 27. But in our case, we slightly shift the minimum Gibbs energy point by considering the coordination number of the binary and then interpolation method. You can see without any ternary parameter, we can explain the carbon solubility data. As you know, this carbon graphite Gibbs energy, we use the same value. It means to get this Riccius line, carbon solubility line, we should have similar Gibbs energy level with the Bragg-Williams random mixing model. But they added very, very big parameter without considering. So titanium, vanadium, aluminum system should be similar. Titanium, vanadium is ideal. Aluminum, titanium, aluminum, vanadium should be very, very negative deviation. So if you consider this kind of the geometrical impact, maybe we can easily solve many problems. So titanium vanadium is very simple binary without any compound. It means we have very, very small interaction. So we can easily explain that. And the aluminum, titanium, maybe you can see in steel database, you can also get the same phase diagram, but we slightly modify the liquid phase, the enthalpy, integral enthalpy of mixing. And aluminum vanadium, you can see from actually, because I left the academia to join the research institute and the company, so I couldn't update that. But if you can see from COST 507 project, steel database have this dashed line yet. So maybe we have to update that. So maybe next version or steel database you can see. And by merging this one without considering this asymmetricity or asymmetry of the Ricci solution, you can see 280 kilojoule or sometimes minus 550 kilojoule. That should be just a fitting parameter. Without considering this asymmetry, they need to tilt the Gibbs energy plane inside this ternary triangle. But I didn't put my parameter, but after the publication, maybe I'll share that. But we added only one single very small ternary parameter to explain the ternary, the Riccius temperature. So based on this thermodynamic database, we try to use that for the prediction of some physical property, the molar volume change depending on the temperature and composition. So you can see if you have ideal, manganese ion is very typical ideal solution. So your molar volume can be changed by just proportionally. But if you have negative deviation, it means silicon and Fe like each other. So you can expect the volume shrinkage during mixing. So this dashed line is kind of the mean volume from silicon to Fe. So if you have negative deviation, you have kind of the shrinking tendency like this. But if you have positive interaction, they don't like each other. It means when you mix these two, the volume will be expanded. So this simple concept, I didn't name this equation like Thibodeau and Zhang's equation for the diffusivity, but I suggest that kind of the Paek and Zhang equation to Professor Ino-Jung. I'm not sure, but I think it's impossible. It's too simple. So molar volume can be calculated by the sum of the pure A, pure B, and the specific volume of the AB pair can be easily calculated. So because we know this pure volume of A and B, we can calculate the AA pair, BB pair, and AB pair by the Fax-Age modified Quasichemical model. So if you have idea, your the specific volume of the AB pair should be almost the mean volume of the A and B. If you have a bigger than this mean volume, you will have the positive the deviation, and much smaller one, you can expect that the shrinkage and then the negative excess Gibbs energy. So by using very, very simple equation, we can predict that. So before that, we defined the temperature dependence of the molar volume of the unary system. And luckily, my colleague in DLR, Professor Brillo, they measure the density and surface tension of the titanium, vanadium, aluminum subsystems. So but titanium, vanadium is very simple ideal solution. So we can easily explain that. So you can see from the Fax-Age titanium, vanadium binary system, we can easily extract the titanium-titanium pair and the vanadium-vanadium pair and titanium-vanadium pair like this one. And then using this very simple polynomial, because we know the pure vanadium, pure titanium volume and its temperature dependence, and we have this experimental data, and we can also calculate this titanium-titanium, vanadium-vanadium pair number, pair fraction. So, and also we know this one, we don't know only this parameter. So by plotting all this experimental data and extracted value against this the mole fraction of the titanium vanadium pair, we can calculate this number, which was very similar like a mean volume. So it should be ideal. So I want to introduce how you can get this bond fraction, pair fraction. If you open the equili file, the parameters, you can click this one, and then you can see what is the bond fraction of your Rickey solution. And then I don't know, you click this XML the button or not. If you click this one, you can select the bond fraction, and you can get this kind of curve. Okay, so if you use the STIL database, everyone can get this kind of the bond fraction. And previously, we have to extract this bond fraction data from XML file, but because this with Jean-Philippe 10 years ago, how to extract this one. So without app, I can, if you double click this line, you can extract all this data by the Excel file. I didn't know that. So yeah, please update that if you upgrade the Fax-Age. So aluminum titanium system, unfortunately, we don't have overlap temperature range. So aluminum, because of the aluminum vapor, high vapor pressure, like this one. So, but titanium melting temperature 1663 or 8, I don't remember. So because they should have some kind of the undercooling effect, but they couldn't reach it to this temperature. So I tried to reproduce the molar volume change, but aluminum rich side was reasonably okay, but titanium rich side, you can see the scatters like this, big deviation. It can be because of the oxygen content, as I mentioned earlier. If you can see, we also measure the oxygen concentration in liquid aluminum, but if you decrease the temperature, our oxygen solubility, dissolved oxygen content can be almost 10 ppm. So these data, maybe they should control the oxygen atmosphere, and then their extracted the density include only just the 10 ppm level. But if you can see the titanium from iron to titanium rich side, maybe you will have much higher oxygen concentration, 1%. So if you have oxygen dissolution, you cannot get very accurate density and surface tension. So you have to consider the oxygen potential or partial pressure, and dissolved oxygen concentration have to be considered. So similar method, aluminum titanium, maybe you can get this one. And we have slightly negative deviation. And aluminum vanadium, yeah, unfortunately we cannot get this overall temperature, so also have the problem of the oxygen level. And aluminum vanadium, yeah, should be, yeah, we can extract the pair fraction data from FACSAGE, and you can see, yeah, we have to just trust the aluminum rich side data to get this aluminum vanadium pair fraction volume. And then recently, one of his PhD, he measured the equimolar composition of the titanium vanadium. They increase aluminum and then measure the density and the surface tension. So we already have the temperature dependence of all the volume and volume of the pure component and all these pair fractions volume. So, and also from this composition to this composition, we can get all the distribution of the pair fraction. So simple, just the plus, minus, and multiply something. We can simplify this equation. And if you have all these numbers, we can just follow the trend. But I didn't consider the oxygen yet because we have to check the oxygen solubility and oxygen parameter. Maybe after summer, we are doing some equilibrium experiment to measure the equilibrium oxygen solubility in vanadium rich site. But you know, the vanadium melting temperature is really high, so not easy to measure that. So yeah, that's very simple suggestion to calculate the molar volume using modified Quasichemical model. Yeah, but we have a limitation of the oxygen, but you know, we have to add oxygen-oxygen pair volume. So this can be the hypothetical the parameters. So help to get as many as possible all the experimental data. So after the oxygen, maybe we can apply this one to the surface tension calculation, and then the 3D printing, additive manufacturing simulator, we can use this database and then the physical property. Okay, that's all. Thank you very much.